two more talks coming up. The first one is by Gabor Csathy from Purdue University about paired and type phases in 2DECs. So go ahead, Gabor, the floor is yours.
Thank you. Let me see if, here we go. So now, well, I'd like to thank Andre for doing the lion's share of the work and for the staff at Stony Brook to keeping us afloat. So in this talk, I'm going to be interested in the Half-field Landau level. And so we have seen that a lot of interest in the fractional quantum Hall effect at a filling factor 5.5, for example, also seen on this trace down here. But what I'm going to show you is that under certain conditions, there is a competing ground state, the stripe phase. And I guess the first thing that I'm going to tell you is that we discovered this initially putting high pressure, hydrostatic pressures on the sample. But later on, we've shown that the stripe phase is also present at ambient pressures. So I'm going to tell you now how we get to the stripe phase and what are the special properties. I think why this is interesting. Now, this work started in 2016, and this is just like a recent review that I wrote with my former student. So I'd like to quickly acknowledge Nodar started this project, but really most of the work was done by Catherine Schreiber. And I like to acknowledge the samples, which I have two samples, one from Michael Manfred and one from Lauren. And most of this work was funded by the DOE. So this is a quick review slide, pretty busy, but perhaps I don't need to spend a lot of time on it. We are looking then at the Half-field Landau levels, and at the orbital quantum number 0, we're going to have the Fermi sea of composite fermions. At the orbital quantum number 1, we're going to have the fractional quantum Hall effect. And then finally, in the high Landau levels, we're going to have the stripe phase. So this is specifically at filling factor 1/2, or a half-field Landau level. And I guess I like to focus a little bit on the nematic phase. So I'm going to call this the quantum Hall nematic, or the stripe. So initially, Kulikov, Folger, and Shklovsky, and then Mosner and Chalker basically had this kind of, order in mind. But later on, it was realized that, you can break just the rotational order, and in that case, you would have a nematic phase. So in transport measurements, we can only be sensitive at the breaking of the rotational symmetry. So we don't really know anything about microscopic order, but I'm just going to assume going forward that we have this kind of filamentary arrangement where the size of these filaments, the lateral size, is close to a classical cyclotron radius, or a couple of magnetic length, depending on which Landau level you may populate. Now, whenever we say nematic, we already encountered, different kind of concepts. So even just today, Kun Yang talked about nematic Fermi sea. We have nematic fractional quantum Hall effect. So the quantum Hall nematic, then it's different because we have this kind of charge ordering. And, there's also other kind of liquid crystalline phases, in other materials, perhaps somehow related to these. All right. So I'm going to then use the term stripe and quantum Hall nematic interchangeably. And I already told you about the different kind of ground states, right, at half filling. So some kind of silly representation of them right in the middle. But I also kind of want to ask the question, what happens away from half filling? And so if you're in the lowest Landau level, the top line, away from half filling, of course, we have a whole sequence of fractional quantum Hall states. In contrast, if you go to high Landau levels, we only have these kind of charge order phases. In particular, if you go away from half filling, those would be the bubble phases. And we also heard, for example, about bubbles in graphene in the first talk on this conference. And the interesting thing is that in the second Landau, just a quick reminder, we have both of these. So we have fractional quantum Hall states, and we also have the bubble phase. So this is kind of interesting because the bubble phase and nematic, or the bubble phase and the stripe, always seem to show up in pairs. So whenever, in fact, they were discovered in the same experiment. And so one then may ask, since the bubble phases are present in the second Landau, is it possible that the quantum Hall nematic also will show up? Well, it's quite interesting that the fractional quantum Hall state at 5.5 was studied for, more than 30 years, and somehow this nematic never showed up. But I'm going to show you that, within reasonable, parameter space, we can access this particular ground state. Now, this question is not, completely unexpected, meaning whether the nematic could be stabilized at Philip factor 5.5, because we know that the ground state, the fractional quantum Hall ground state at 5.5 is very close to a nematic. So for example, in these early experiments, when the 5.5 state was tilted, so there was an in-plane magnetic field added to the sample, there is quickly a nematic phase developing. So at an in-plane magnetic field 0, we have isotropic ground states. Okay, so, but when we apply an in-plane magnetic field, there would be a nematic state. Now, how exactly this nematicity, appears, may not be that simple. So if I kind of were to summarize everything that people have seen, probably it's fair to say that at small tilts, the fractional quantum Hall state survives, but it's going to be anisotropic. So that will be a nematic fractional quantum Hall state, as shown, by detailed work of Mansur-Shahagan. And then eventually, when you increase the tilt, you're going to basically close the gap, and some kind of a nematic phase is going to show up. Now, what about that 0 magnetic field? Well, this is an interesting experiment in 2014, where there was a very low density sample, 5 times 10 to the 10, and high mobility. And so what they've seen, Wei Pan and then Tsui, what they've seen is that filling factor 5.5, there is an incipient fractional quantum Hall state, but at filling factor 7.5, there is anisotropy. Now, the interesting thing when you read this paper is they never call this ground state a stripe, even though they use this term for the 9.5 and 11.5 and other states. So they just call this an anisotropic state, and perhaps the data quality kind of didn't ensure drawing a conclusion, but this is already indicative that nematic instability perhaps can also occur in a purely perpendicular magnetic field. So let me first talk about our experiments at high pressures. These would be hydrostatic pressures. So we're going to be just shrinking the crystal in all directions with a setup such as this one. And so we're going to have a pressure transmitting fluid basically in a syringe. So we're going to kind of compress the syringe, this purple part's going to push down. We're going to increase the pressure to, okay, I call it high pressures, this is not a diamond Enven cell, so perhaps you can call it, relatively high pressures of the order of 10 kilobar or 1 gigapascal. And the sample that we're going to be using would be a kind of standard high mobility 30 nanometer quantum well, in which the fractional quantum Hall state at 5.5 is, known to be, the strongest, kind of a sweet spot for this. And I'm not going to spend more time how the setup works, but we have pressure measuring devices, pressure gauges, and we actually also have a little LED inside this pressure gauge. So what does pressure do? Well, pressure is going to be basically changing the lattice constant. So it's going to move the atoms around. It's going to shrink the lattice constant. We're going to change the Bloch wave functions, and hence all the properties that go with this. Obviously, the effective mass is going to change. But because we're changing the energetics, the density, in particular in the gallium arsenide, the self-consistent solution to those equations is going to shift. And so as we increase the pressure, so this is a kind of a strange plot because the pressure is on the top axis and the density is on the bottom axis. These two quantities depend linearly. So as the pressure increases, the density actually is going to go down. Keep that in mind. And of course, as the density decreases, the mobility will also drop. So depending on how much time I have at the end of the talk, I may be discussing a little bit of this, but keep this in mind that the density is not a constant. And so this is basically a basic data set. We're going to be measuring the resistance along two orthogonal directions, basically on the square of Vanderbilt sample. And at 0 pressure and up to about 7 kilobar, what we see is that at least in the middle range of this filling factor, close to 5/2, the resistance is almost isotropic, particularly at 5/2 is quite close to being isotropic. And there is a fractional Coulomb hole state, even though I don't show hole quantization on this plot. But if we increase this pressure just a little bit, suddenly we're going to hit the nematic phase. And notice that the resistance anisotropy is quite large. So for example, at this particular pressure, the resistance in the what I call the YY direction, so it's one particular Christoforth axis, is more than 1 kilo ohm. And so this is the basic data set. So we know there is a nematic, and then there's all kinds of questions now we like to address. You certainly want to know how close is the nematic to the fractional Coulomb hole state. But before getting into that, so this was the first time basically when we've seen the nematic state developing or the stripe phase developing at filling factor 5/2. Now, the first question I'd like to answer is pertains to basically a little bit of discussing the particular shape of the resistance anisotropy. The second thing I'd like to kind of convince you is that we think that we don't really have any in-plane magnetic field. And so just a quick reminder that so far I talked about the stripe phase at filling factor 9/2 and higher whenever there is no in-plane magnetic field. So this is, what I would call a spontaneous stripe or a spontaneous nematic, meaning that I don't apply any external field in order to break rotational symmetry. And then we also have the nematic phase, or perhaps different kind of nematic phases that develop when the sample is tilted. And so I'm going to call these kind of nematic phases induced nematic, because you actually need this external symmetry breaking field applied to your sample to induce nematicity. And so the interesting thing is that here the anisotropy develops over a limited range of filling factors, whereas in the other case, when you have an in-plane magnetic field, suddenly the anisotropy basically develops everywhere where the resistance is non-zero, at least what you can see in the experiment. So I'm going to now compare the stripe phase at 5/2, and you can clearly see that the range of filling factors is very narrow. So this allows me to conclude that the signatures that I see in the resistance is really similar to the nematic or the stripe phase that develops at filling factor 9/2. And so that leads me to conclude that there is a good chance that we don't have any in-plane magnetic field. So, well, we don't apply any certainly, but, occasionally the sample, could do funny things in that pressure zone. And so in our experiments, we don't have, I believe, such an in-plane magnetic field. Of course, this is kind of expected. If the sample stays the way we placed it, applying hydrostatic pressure is not gonna induce any breaking of the rotational symmetry. So it kind of makes sense that the resistance is unlike the one that's induced by the in-plane magnetic field. Now, of course, we can also do very simple tests when we plot out how the density changes with the pressure. And if the sample somehow tilted inside, we're just going to find that the apparent density, or the magnetic field at which that particular fractional Coulomb hole state develops, is just going to be off this straight line. So we know that we don't have any major deviations from the perpendicular. So the magnetic field is truly perpendicularly applied to our sample, within our error measurement. So we, of course, then can go and take data at several different pressures. And what you see here is RXX and RYY, so the two longitudinal resistances. The blue areas are the zero resistance. So this is a fractional Coulomb hole state, 5/2. This is basically in the other direction. And eventually we hit this big red peak. That's the stripe phase. I guess it's a bit easier to kind of follow on the right-hand side. So the resistance is 0, kind of deviates from 0, and then goes into this large blue basin. That's the stripe phase or the nematic phase. So let me just label these. And okay, so the data, has a lot of features, but let me just focus at half filling. And so what we see is that the fractional Coulomb hole state is contiguous to the stripe phase. So this data suggests that there is a direct quantum phase transition. So we go straight from the fractional Coulomb hole state into the stripe phase. So this is actually very interesting for several reasons. First of all, this is then an example of going from a topological state to a phase that it's a conventional Landau phase. Now, this is, not the only kind of example that we have. For example, filling factor 1/5, we know that we can have a transition into the Wigner solid, but these ground states that we have are really special. The fractional Coulomb hole state at 5/2 is not a garden variety fractional state, and similarly, the charge order is certainly a very special charge order. So this kind of quantum phase transition that's driven by the pressure so far is a pretty interesting one. And so, let me then take a look at the energy scales that are involved in this problem. So here we have the red line is the energy gaps for the fractional Coulomb state that we measure. And then the blue line is, or the dots more specifically, is the melting temperature, if you like, of the stripes. And this plot shows you how they depend on pressure. And so this is basically at temperature equals 0. We think that we have a direct phase transition from the fractional Coulomb hole state to the stripe phase. And I guess, if you like, you can also think of this kind of plot a little bit as a phase diagram. So certainly this boundary is pretty sharp here. So if you go above it, you're going to melt the stripe into a firm liquid. Now, this other boundary, of course, in contrast, is not sharp. So as you heat up the fractional Coulomb hole state, you're going to generate excitations, and then eventually you're going to have a crossover. So here we're going to have some kind of a broader range where we're going to cross over into firm liquid. But nonetheless, I think that this data is suggestive, first of all, of this quantum critical point, which is around 7.8 kilobar in this particular case. And it basically is telling you that, yes, so I told you that there is a fractional Coulomb state. I told you there is a stripe phase, but they have an interesting relationship. The phase diagram is not the way I've drawn it. Actually, you can also draw other different geometries here, but the suggested phase diagram is this one that at t equals 0 has a direct phase transition into the quantum hole nematic. So this is interesting because, well, first of all, this, at least in the kind of zero in-plane magnetic field case, the one that I discuss here, it only appears for the fractional Coulomb hole state at 5/2. At 7/3 or 8/3, we don't have this nematic state. So clearly, this transition is very specific to the paired nature of this fractional Coulomb hole state. It's also very interesting that, as far as I know, for the stripe phase, we don't really need to invoke the existence of composite fermi. So we think of the stripe phases as made up of electrons. Whereas if you go left of this quantum critical point, the critical pressure, everything that you would see there would need to invoke the existence of the composite fermions. So this critical point, this critical pressure, then it's very interesting. Somehow you have to make a transition in describing your system from the composite fermions towards the electrons. Now, this of course going to have very interesting implications also for the Fermi liquid. We always think that the ordered states come out of a Fermi liquid, but then the question is, as you go down on this wedge towards the quantum critical point, you're going to be basically surrounded by basically the system that either asks you to use composite fermions to treat it, or it requires you to think of electrons. So this Fermi liquid that's basically wedged in between these two phases may have some interesting structure. So, all right. Now I told you that the density changes, and so the critical pressure is a little bit less than 8 kilobar. The critical density then would be about 1.1 times 10 to the 11. And of course, this kind of begs the question, what have people seen at filling factor 5/2 at this particular density? And here, I have some collection of data. This density, of course, it's a bit higher, 1.6, clear fractional Coulomb hole state. This density is a bit closer, but now it's below. And then we have even, other lower densities. The bottom line is that, of course, there is always, in these earlier experiments, there's always a fractional Coulomb hole state developed. There's always a gap. So that, of course, then begs the question, what is the pressure doing in this case? Now, one thing that may help us is considering the behavior at 7/2, cousin state. And notice that at this pressure, which is below 6 kilobar, okay, we see the nematic phase at 11/2, 9/2, and 7/2. So this is not a mistake in labeling, but at 5/2, we have a fractional Coulomb. So this is a very unusual plot because we used to see always fractional Coulomb host states at both of these filling factors. And so now we somehow have broken that symmetry. And now if you're going to increase the pressure even further, then eventually the nematic phase also is going to show up at filling factor 5/2, as I discussed it earlier. So this is kind of expected. We know that these two filling factors are similar in a lot of respect, but one thing that we conclude is that the critical pressure for nematicity, the quantum critical point, will occur at different pressures at 7/2 and at 5/2. So I'd like you to keep that in mind. The critical pressure at 7/2 is about 6 kilobar, a lot less than 7.8 kilobar at filling factor 5/2. So so let me then just discuss a little bit of some theoretical underpinning of this. This is a paper by Rezai Haldane in the year 2000, where they basically looked at the Moritz state, and they basically figured out what happens if you change the pseudo potentials a little bit. So here we have the width of the quantum well, basically. So they tune the pseudo potential eventually with the width of this quantum well. And so what you can see is that the overlap was significant at these widths, but then for very narrow width of the quantum well, basically the overlap, got very small. Now, later on, there were a lot of these, similar studies, but the interesting thing they did, they asked themselves, what would be then the ground state whenever at filling factor 5/2, whenever the overlap with the Moritz state is not high. And so what they find is that you're going to have a charge density of a stripe phase. And this would be kind of a diagram when you change two of those pseudo potentials, number 1 and number 3. And then you're going to have a boundary between the paired state and the stripe phase. And you're going to cross this boundary. If you kind of do an experiment, you may imagine different ways of doing it. But if you cross this boundary, then obviously you're going to see a direct quantum phase transition between these two phases. The interesting thing here is that if you go to the pure Coulomb interaction, so 0 and 0, you see the stripe phase is stable. So of course, that is kind of consistent with the fact that at the limit of 0 width, you're going to have basically no fractional Coulomb state within this model. You need a finite width to stabilize the paired fractional Coulomb state. Now, later studies, interestingly enough, kind of forgot about the stripe phase. So for example, here we have work where, of course, people were interested in the fractional Coulomb state. So they studied how, say, the overlap will change, let's say, if you increase the number of electrons and so on. So here, for example, we have the 5/2 state. Again, at low width, we have poor overlap. And, but the width parameter is not the only parameter that tunes these states. We know that Landau level mixing is an important parameter. So over the years, we learned that as the Landau level mixing parameter increases, the overlap functions will decrease. But, no one really looked carefully what would be the ground state, basically once the overlaps become, small enough. There's basically some studies here that then they would also kind of do both of these parameters, the mixing parameter and the width parameter. And then, this particular plot, for example, plots the excitation gap, but, there's a similar plot they have also for the overlap of the, exact wave function and the numerically obtained wave function. So the bottom line is that now we have two parameters that can tune the fractional Coulomb state at 5/2. So we like to kind of think and, kind of figure out where are we for the nematic phase whenever we tune these parameters. So this is then a plot of the Landau level mixing on the horizontal scale and the width on the quantum well, dimensionless width on the vertical scale. Basically, for all the samples I could find in the literature prior to our work, in which there was a fractional quantum Hall state developed. So these symbols are places where fractional quantum Hall states have developed. Oftentimes, when you just take a sample and tune the density, you're going to get these kind of lines that you see, these streaks. The reason for that is that if you tune the density, then kappa and the width parameter are not independent. Of course, you can quickly figure out that if, let's say, if you just assume that the effective mass doesn't change, then the width scales with the magnetic field in a certain way, kappa scales with a certain way square magnetic field, and then, of course, you're going to get, some kind of a hyperbolic relationship here. And so our sample, which is under pressure, is these red dots. So these are the fractional quantum Hall states that we have. And where is the nematic? So the nematic, it turns out that it's in this region where basically the fractional quantum Hall state was not accessed before. And so this is quite interesting. This was basically the first time that it gave us the idea that maybe pressure is not that important in bringing out the nematic. Well, I told you, remember that we are tuning the density a lot whenever we tune the pressure. So maybe the density somehow drives this transition. But of course, the answer cannot be as simple, because I showed you that, samples that had densities close to our nematic transition, close to the sample, close to that of our sample, close to this transition, didn't see the nematic in prior experiments. So somehow these parameters have to play a role. Now, in order to kind of really nail this, what we did, of course, we can compare what is the role of these two parameters whenever we look at filling factor 5½ and filling factor 7½. And so the open symbols are the fractional quantum Hall states as we increase the pressure. The closed symbols are the stripe phases at high pressure, and then the green dot is this quantum critical pressure, corresponds to this critical value. And so what you notice is that even though the transition to the nematic at 5½ and at 7½ occurs at different pressures, the same transition, when looked at this parameter space, actually occurs at the same value of WLB and the same value of kappa. Okay, so this already suggests that these parameters, therefore, have to be important. And so let's kind of look a little bit. So the stripe phase then would be stable at low values of W over LB. So this is kind of similar to what the theory has seen. At low values of this parameter, the bridge state would be unstable. The overlap functions would rapidly decrease after a critical value. And so this is kind of consistent. We have now a number for this particular experiment. And then similarly, the stripe phase would be stable whenever kappa is large. So in our case, kappa has to exceed something like 1.8. But of course, we don't do cuts at constant kappa at constant W. So the way our experiment is done, both of these parameters change, the way you have seen it. So this is then suggestive that these parameters are indeed driving this transition, if you like. And so in order to really make sure that this is the case, what we wanted to do is engineer now a sample, which not under pressure, but under ambient conditions will have these kind of parameters. And so
Gabor, you've got about 2 minutes left.
Oh, sorry. Yeah, I will be able to do that. So this is now a sample that has 0 pressure. It's a 30 nanometer quantum well sample. The only thing that we have is that the density is about 1.1 times 10 to the 11. So what you see is that at 7½ there is a huge nematic phase. At filling factor 5½ we have, well, the behavior is pretty complicated, but certainly right at filling factor 5½ we have an energy gap. The resistance vanishes. So putting this on the diagram that we have before, but this time for a sample at 0 pressure, what we find is that the 5-half filling factor happens to fall in an awkward spot. We just were not careful enough to design this very well. But the 7-half filling factor falls deep into this nematic phase. And so basically what I'm telling you is that, yes, pressure brought out these kind of phase transitions, but that was just fortuitous. In reality, what you really just need to do is tune these two parameters, the width and the Landau level mixing parameter. Now, I just need to quickly mention that the nematic phase at 0 pressure in the sample has a huge resistance anisotropy. It goes up to like 4 Coulomb. However, you also need to keep in mind that we were just lucky that we have a extremely low temperature setup. This was a temperature close to about 4 millikelvin. And by the time you reach a temperature like typical temperatures, 10, 15 millikelvin, the resistance anisotropy disappears. And maybe in the question session, I can maybe talk a little bit about what we think at this point. Now, in order to kind of wrap up, yes, we know these parameters are important, but what's the meaning of all this? Well, it turns out that these two parameters, the Landau mixing parameter and the width parameter, really tune the effective interaction, as you know, in Haldane work. But specifically, what we know is from the theory that we are tuning actually the short range part of the interaction. So what I told you is that the fractional quantum Hall state and stripes are basically very closely related. You have a direct phase transition. And now through these parameter studies, we can say that indeed the transition actually occurs when you tune the short range part of this interaction potential, which I think is a very interesting conclusion that one can draw. Very quick, I'm going to mention that related bubble phases, so this is no longer at filling factor 1/2, bubble phases have been seen in graphene. We have seen early talk. This is from data from Corey Dean. But it's interesting that at filling factor 1/2, there is no stripe. Well, I don't think that we really know what is the exact reason. One reason could be that graphene, doesn't have the same symmetry as gallium arsenide. So we have a, threefold symmetry here. And maybe just the nematic domains don't really know how to order. Another reason could be, according to the previously presented data, maybe these parameters, the mixing and the width parameter, where they have less control, of course, than in the gallium arsenide cycle, maybe those parameters are just not tuned to the right place to observe any kind of nematic phase. So with that, I'd like to just put up my conclusions very quickly. We see nematic phases at filling factor 7/2 and also at filling factor 5/2. The interesting thing about these nematic or stripe phases, they're right next to the fractional quantum Hall state, meaning a very small change in a parameter. We have shown it with pressure, but probably other parameters we suggest would drive this kind of phase transition from one phase to another. And what we figured out is, based on our data, is that tuning of the short range part of the electron-electron interaction is critical in driving this transition. So with that, thank you very much.
Thank you for a great talk, Gabor. Let's keep the questions for the Q&A session and keep going immediately.
Absolutely,
with
yes.
the next talk.
Thank you.
So the next speaker is